Okay, so this is a question that a student had asked, and we wanted to go over this. And in the office hours, I was having technical difficulties. So I said I would go over at the beginning of class. And it looks like a great problem to go over. So I wanted to start the recording and do that. And so the question says that we have the limit as x approaches 7 of this f of x minus 5 in the numerator all over the quantity x minus 3. And we're given when we find that limit, it's equal to 3. And it's asking us then to find what is the limit as x approaches 7 of just f of x. Okay, so let's go and use this, what they're giving us. Let's put this in what we know. So when we're taking the limit as x approaches 7, we can go in algebraically and we can go plug in 7 wherever we see an x in that function. And so when we do this, I'm just going to write 7 here and here. When we do this, we have f of 7 minus 5 all over 7 minus 3. We know that that limit right there is equal to 3. I plugged in the value that x was approaching, so when I wrote the step on the bottom, I don't rewrite the limit value. And so let's get what f of 7 is. And so let's solve for f of 7. So let's simplify a little bit. And so this is saying that we have f of 7 minus 5 all over, well, 7 minus 3 is 4, is equal to 3. So let's get rid of the fraction. We can do that by multiplying both sides by our denominator of 4. And so when we do that, we get f of 7 is minus 5 is equal to 12. Isolate the f of 7, we want to add 5 to both sides. So then f of 7 is equal to 17. And so now, right here, when it says find the limit of x approaches 7 of f of x, this should equal f of 7. And we just found that below here what f of 7 was. F of 7 is the same thing as 17. Okay, so any questions over the steps of that? Does that clarify and kind of figure out where you were missing? And so there's a question on the chat, so let me just read it and then I'll answer it. So you treat it as a variable pretty much and don't worry about the 7, the x value. Well, when you're taking limits, basically this is telling you what value you're going in and plugging in for x. And here, so here when it said find the limit as x approaches 7 of f of x, and we go back in and plug in 7 here, we need to know what that f of 7 value is. And they gave us enough information in here. So when we looked at this problem with the information they gave us, and we went in and put in the limit, we plugged in 7 wherever we saw the x in this function, we could then figure out, with all the information they gave us, we treat this like a variable. We're trying to figure out what this variable is representing. And so basically this is also saying this is when x is 7, as we're getting closer and closer to x equals 7 on the graph, your y value is getting closer and closer to 17. Did that answer your question, Timothy? Okay. Any other questions on that? Let's pull your pictures over here. Okay, so let me pull in. We're still looking at limits. I was gonna hopefully get into the precise definition of a limit today, but there's still a couple things left in that 2.2 sections we've been working on the last couple of days that we still haven't covered and we need to get to. And so let me pull that up for you. Okay, so I wanted to talk about a little bit because I missed this, or maybe I didn't touch on this. We looked at limits, and sometimes limits don't exist. And here's a couple examples on where you would not have a limit exist. And so in this first example, this first graph on the left, notice that you have a horizontal line on the y-axis until you get to the origin, and then that's an open circle. And then you have this jump on the graph, and then you have a solid circle at 0, 1, and then it's a horizontal line at y equals 1. And so all of these graphs represent something where the limit does not exist at 0. And so if you look at this, we said that a limit has to exist if the left and the right hand limit are the exact same thing, and it exists. So if we look at the limit, and it doesn't necessarily exist at the value that we're looking at the limit of, but if we're looking at the limit here as x is approaching 0 on the left, so coming in on the graph, your x values on the left, if you follow in there, our y values are all the same in here, 0, and we're still getting closer and closer to the y value of 0. And they called this graph u of x. Let me just put that in. So the limit on the left as x approaches 0 is the y value is 0. But if we look at this at the limit as approaching x on the right, so our x values are getting closer and closer to 0 on the right, we want to see what's happening to our y value. Well, our y value is getting closer and closer to 1, and it actually equals 1 at that. And since those limits are not the same, then we know that that limit doesn't exist. Same sort of idea here. If we look at the left, when we're coming in x on the left, notice this graph shoots downwards. It's not going towards any one y value. This is of g of x. This is actually equal to negative infinity. I'm just stating that because that just kind of tells us what's going on the graph there, but this limit actually doesn't exist. We could technically just stop there because if the left-hand side limit doesn't exist, well, maybe I should go further, just because I'm thinking of a section later. So what I'm saying might have not been totally true. So let's look at the limit as x approaches 0 on the right. And if we look at that coming in on the right-hand side of the graph, our y values, as we get closer and closer to x equals 0, our y values are shooting upwards and going to positive infinity. The one example I really wanted to look at was the example this next example, because I didn't really talk about graphs, what's happening if we start oscillating back and forth really, really fast. And this is another example of a limit not existing, because it goes up and down so fast as you're getting closer and closer to this value of 0, it's not going to one particular value. Okay. So when a graph oscillates really fast as you approach a value, maybe we can say x equals c, then the limit doesn't exist. Okay, so there's 3 ways we can look at limits. We can look at the graph of a limit, look at the graph and see what's going on as x is approaching some value c, and see is it going towards some y value. We looked at using limit laws and plugging in values for x where the limit is approaching. And then sometimes we have to go in and we actually have to plug in values as x gets closer and closer to the value we're looking at the limit of, algebraically, and just find out what those y values are and see if it is one particular y value that you're getting. So going through the section chapter. I don't know if I said this, I believe I did, but it pretty much followed off of the limit laws, which this theorem says if you have a polynomial and you look at the limit as x approaches c, all we have to do there is plug in c wherever we see an x. And that's kind of what we were doing yesterday when we were looking at limits algebraically. And this theorem 3 also is based off of one of those limit laws that says if you're looking at a limit of a rational function, that's basically the limit of the numerator over the limit of the denominator. It's telling me p and x are both polynomials. So by this theorem above, this is the same thing as plugging in c wherever you see an x in p of x, and a c wherever you see a x in q of x. So we've been kind of just using those theorems, but I don't know if I, again, stated those, so you should have that. Okay. And let me just pause because I think I see a chat on there that I might have missed. Oops. Okay, sorry, it's kind of covered. If there's a hole on the graph, does the limit exist there? If there's a hole on the graph, then the limit does exist there only if the left and the right hand side are coming together. And so, for instance, I can give you a couple different examples of what you're asking. And so the question was, if you have a hole in the graph, does the limit exist? Well, here's an example where it would exist. You might have a graph, it's defined everywhere, maybe, that let's say this value x equals c, f of c is undefined. And so as we look at the limit as x approaches c on the left of f of x, notice that y value we're getting closer and closer to is f of c. And so it is f of c. And the same thing here, as we're coming in on the right, that y value we're getting back is also getting closer and closer to whatever that f of c value is. And so the limit exists. We'll show later in this chapter that because this doesn't equal what actually f of c is, that this is discontinuous there. So in college algebra, we talked about polynomials being continuous functions. They were smooth and continuous. That term continuous, and we talked about, well, that continuous means that you had no jump in the graph. You couldn't pick up your pencil. But we're going to define that more rigorously mathematically. Yeah, so I can explain that one more time. And so here's an example where f of c doesn't exist. It could actually even exist, but be a point up here. But when we look at the limit as x is approaching this value at c, that y value you're getting closer and closer to is the same. And so the limit has to exist. But there are cases where you have an open hole where it wouldn't exist, like a piecewise function. And I think we'll get into graphing these more later on in this chapter again. But so at this value, maybe we have a here is what the y value is. And let's say that this y value here is b. And so the limit in this case, as we come in, so let's say we're coming into the c value on the left-hand side. So go up to your graph, look at the left, which piece is on the left of it, which is this piece. And as you're getting closer and closer to this x value of c, that y value that you're getting, even though it's an open circle there, and we're on the left, let's call this g of x. Of g of x, this is equal to a. And here, this limit as we're coming in on the right-hand side, So looking at x equals c, look at the piece of the graph on the right. So that would be this piece up here. As we come in on the right, that y value you get closer and closer to, which it actually is b. And since a does not equal b in this graph, the limit doesn't exist. So I'm just going to start giving you kind of some notation mathematically that you might see later on, and well, there are kind of tricks to do shorthand. This triangle made with these dots here means therefore. So I can say therefore the limit doesn't exist. So the limit as x approaches c of g of c doesn't exist, or g of x does not exist. Okay, so actually I've pulled a couple of examples that we're going to look at, and we're going to look at an example of finding the limits the 3 different ways and showing that you're going to get that same value when you do that. So let me I'm going to skip this sandwich theorem for a minute. We'll come back and we'll look at some examples of that, but I want to look at this. Okay. So we have the following example. We're given that g of theta is equal to sine of theta over theta. So we're going to find this limit as theta goes to 0 of g of theta, and we're going to show it 3 different ways of doing this. And so part A says make a table of the values of g at the values of theta that approach theta sub 0 equals 0 from above and below. Then estimate the limit as theta approaches 0 of g of theta. Okay, so again, we are given that g of theta is equal to sine theta all over theta. And it wants us to make a table. And we're looking at the limit as theta approaches 0 of sine theta all over theta. So actually, this is an example right now that we would not be able to manipulate. If I went to go solve this algebraically, which is the first thing I would try to do, by going in and plugging in 0 wherever I see a theta in my function, notice what we get back. This would equal sine of 0 all over 0. Remember, sine of 0, that's equal to 0. And so this is equal to 0 over 0, which is an indeterminate form. And that's where this doesn't tell us anything, and we need to kind of go back and manipulate or use a different method to try to find this limit. And so I don't know how to manipulate it. We might get some more tools later in this chapter, but for now, part A wants us to look at what's going on when we get really, really close to 0 on the left. So if I'm getting close to 0 on the left, well, those would be negative numbers, right? So if I have negative 0.1, so I want to see what g of theta is. So I need to go back in here and I need to figure out what is sine of negative 0.1 all over negative 0.1. Okay, so those aren't values that we learned in trig. We're, I believe, assuming that our theta value is a real number and not an angle. And so I have to go and plug that in the calculator. The thing is, I want to plug in a lot of numbers close to 0 on the left, showing as I get closer and closer and closer to 0 on the left, that this y value actually is becoming the same thing or getting closer and closer to the same thing. And so let's choose another number that's closer than negative 0.1. Okay, so negative 0.05, negative 0.01, negative 0.0001. And so it could kind of get tedious, especially if this was a larger, had more values of theta in it. And so this is where we want to go. You want to go use Desmos, or if you have a graphing calculator or function, you can plug in your function. You might want to use it here. You won't be able to use those things on an exam, but for homework and the process of understanding what's going on, you're good for doing that. So let's go in and let's go see what's happening as x is getting closer and closer, oops, to 0 on the left. That looks really bad, sorry. So let me pull up Desmos. And I want to use their scientific calculator. I want to go in here and I want to plug in my function. So I'm going to call it f of x instead of f of theta, just to make it easier. This is equal to, what was it, sine of x divided by x. So if I plug in negative 0.1, my y value becomes 0.017453, ... So let's see if this number is approaching something, the same value, as x gets closer and closer to 0 on the left. So negative 0.05. Okay, so notice here we have 0.017, 0.017. You know, there's a lot of places that we're going out and they're very similar. And so that's telling me that this looks like it's going to one particular value as we come in on the left. Okay, so looking at this, as a limit is approaching x on the left, or x approaching 0 on the left, we're getting a value of approximately 0.017. Okay, so looks like these go to 0.017. I believe that's what I said. But I'll realize that in a minute if it's not. So this is just the left. And so technically I could write this way. So I'm looking at the limit. In our case, it's theta, not x. As theta goes to 0 on the left of g of theta, and this is equal to this 0.017. And so if we can show the same thing on the right, so 0.1 is close to 0 on the right, 0.01 is close to 0 on the right, 0.001, right? And so if we can show that this is the same y value of 0.017, then the limit is going to exist there, and it will be 0.017. Okay, so let me start plugging in positive numbers. Probably just scroll up here and delete the negative. And so 0.1 looks like the same number as below pretty much, 0.5, 0.01. And so this number is also the same. Notice though it's undefined there. We have x in the denominator, just x. And so this function's defined at x equals 0, but the limit is existing. And if I put f of 0 in here, notice that it spits back as undefined. And so when we plugged in these values, x approaches 0 on the right, we got the same thing. Okay. And so therefore we can say that the limit as theta approaches 0 of g of theta, which is the same thing as sine theta over theta, sorry, this should have been a theta goes to 0 here, not x goes to theta. And this should be g of theta. This is equal to the 0.017. I'm wondering if we can even say it gets closer and closer to 0. Let me just go back real quick. Yeah, it looks like it's still going to the same value. I don't think it's going to get closer and closer to 0. But I mean, technically, we can add more and more zeros in there and never ever get to actually theta equals 0. Okay, so let's look at part B. So part B says support your conclusion in part A by graphing G near theta sub 0 equals 0. And so we want to graph G sub theta equals sine of theta all over theta. And we want to look at the limit as theta is approaching 0 on that graph. Okay, so again, I'm going to pull up this function on Desmos. And we're going to use a different feature, the graphing feature. And so we don't have to put the g of theta in there. It's going to tell us something's wrong. I'm actually going to put sine of x divided by x. And so as we're coming into 0 on the left, oops, is that what function we had?
Yeah, it was sine of x over x.
Yeah, because doesn't that look like it's equaling 1? Let me look at the other piece. Let me see if maybe it was thinking I was doing degrees instead of radians. But right here, this graph is telling me it's not. I know it's undefined there at 0, but it's telling me that my limit is 1. Okay. I'll pull that back in a minute. Oops. Okay, so x is equal to sine of x divided by x. Aha. Notice here, it was on degree. Let's see what happens. Sorry about that. And I even mentioned that you probably should have it in radians. So let's see what happens as we come in on the left into this function. So f of negative 0.1. I get back 0.9999, or yeah, 0.9983. F of negative 0.01. So let's start adding a lot of zeros after that decimal and before the 1, and notice that you're getting back 1. Where if I came in on the right, so 0.1, 0.01, notice we're also approaching that y value of 1. So let me go back here, and there's just a good example. You got to make sure your calculator is in what they want, either degrees or radians. And that's a good way to show that they're not the same thing. You won't get back the same value. Okay, so this should have said 1. This is equal to 1. So coming in on the right, we also saw that it was equal to 1. And since the left and the right are the same, it's equal to 1. Okay, so we actually are going to get a great tool later. I think it's this chapter, it could be the next chapter. It's called L'Hopital's rule, that we could have done this with using his rule without having to go through this process. And we can prove that this limit as theta goes to 0 of sine of theta over theta is 1. But we did show it with showing points arbitrarily close to 0 on the left and the right and getting the same values. They said to graph it. I just pulled that picture from Desmos by copying it on the snippet. Oops. I might not. Oh. I'm not going to go back and graph it again, but we had something right here, right? That this was 1, and we saw that this graph came up here at 1. And so as we're coming in on the left, we're coming in on the right. This was actually an open circle because it's undefined there. The limit as theta approached 0 of g of theta also equals 1. Okay, I wanted to go through that one because that's one that we're going to use this information later on in this course, the sine theta over theta, that's equal to 1. We're going to try to manipulate something to look like that so that we can find the limit. The other one that we're also going to look at later on and use this piece, that the limit of this goes to something. So we're going to also look at this piece. So if we had something in the form of 1 minus cosine t over t squared, I'm wondering if I can pull this. Oops. Sorry about that. Let's try this one more time. Maybe you guys can be writing, why does it do that? 1 second. I'm going to stop share for 2 seconds because I think I might be able to do it without that stop share on there. No. There we go. Try again. If you don't succeed, don't give up. Hopefully you'll eventually get there, but you won't know if you don't continue to try. Okay, there's a plug for working hard in your classes. Okay, so we want to look at the following. We're kind of going to do it the same way that we had just done it. We're going to try going in, plugging in values for t. As t gets closer and closer to 0, of g of t, and g of t is the function 1 minus cosine of t all over t squared. So you're going to go in here, you're going to plug in values.
Are you supposed to share your screen?
Yes,
Sorry.
I am. Thank you, Jason, or I think that was you. Okay, so I just pulled the problem and brought it down from above, and we're looking at this limit, and we're going to now go in and we're looking at the limit as t approaches 0. And so we want to look at what's going on as t approaches 0 on the left of g of t, which was 1 minus cosine of t all over t squared. And so numbers that are close to 0 on the left, we can think of it as negative 0.01, negative 0.001. So just plug in numbers at getting closer and closer to 1. And if you can show that you're getting the same value back each time, or you're getting closer and closer to the same value as you get closer and closer to 1, not 1, 0. I'm writing 1 while I'm saying that. Then we can say that limit exists and it's equal to that value. I'm also going to have to make sure that this is the same thing as if I was plugging in values on the right of 0. So 0.01 is close to 0, 0.001, right? Okay, so this is the limit t approach 0 on the right of this function. So let's go in again and define this function in Desmos, and then let's go plug in these values close to 0 on the left and the right, showing that you're getting back 1 result. So here we have f of x. This is equal to, I need to put parentheses around the whole numerator because there's more than one term. And I believe that was 1 plus cosine of t. And we're using the variable x here. Technically, I could put in here if you wanted to, t, just like the variable they had over there.
I think it's 1 minus cosine of t.
Thank you. I wasn't sure if that was a minus or plus, minus. And then all divided by t squared. And so let's just go make sure that our calculator, I hope, is in degrees. Not degrees, I mean radians. Yeah, it is. Okay, so looking here at negative 0.1, I get 0.49958. That looks kind of close to 1/2. At f of negative 0.01, I get 0.49999, so a little more nines after there. Why is that happening? I'm not sure why that's happening right now. But 0.01, 0.1, because what's this telling me right now? Something's wrong. So let's look, because there's a jump, right? If this is correct, what this function is telling me as I plug in values, getting closer and closer to 0, there's a jump from 0.49 to 0. So let's go and look at what's going on graphically and see if we can see it that way, because that was part B of this problem anyways. I'm actually going to leave that piece in there so we can jump back without having to plug it in again. Okay, so our function, this was the cosine of x minus 1. That's all in parentheses, divided by x squared. Because that even doesn't even look like what we had gotten before, right? Because I think we were getting positive values back. I got to go back and see. But this does looks like, you know, as we're getting closer and closer, negative 0.5, our y value. Looks like it's undefined there, which makes sense because if you plug in 0 in the denominator, it's undefined. But it looks like we're getting our y values here of negative 0.5. Let me just go.
Isn't the 1 a positive?
Did you say
Yeah.
this?
Yeah, it's 1 minus cosine x.
There, that could be my problem. Okay, so 1 minus cosine of x. This gives me this right here. And it's approaching 0.5. Let's go back. I don't think that's what I wrote before. Maybe it was. Yeah, I did. And so notice here, and these were positive 0.5. So I'm not sure what's happening right here and why that's spitting out this is as 0. But that's interesting to me. And if I find out why that happened, I'll let you know. But we could kind of see that this was going to 0.5. This also went to 0.5. Or 1/2. We might see it as more. And this is the limit as t approaches 0 of this function because left and right are the same, but there's an open circle there because it's undefined. We're still getting closer and closer to the y value of 1/2. And then we supported that occlusion by graphing it. I do have this on my graph, so let me pull that up. Let's see if it works this time. Let me get this back. So limit as t, in this case it really says x goes to 0. Left hand equals the right hand, which is a y value of 1. Okay, so one extra concept that we need to know from this section, and then we get to move on. And so let's look at this. And it's called the sandwich theorem. So basically, sometimes we might not know what the limit is. We plug in some value when we plug in, you know, what the limit is going to. And we have some problems, or we don't want to even do that. Oops, let me get to the theorem, sorry. Okay, so this is what the sandwich theorem is saying. If you're trying to find the limit as x is approaching some value of f of x, and maybe it's a hard function to look at, then we might be able to break it down into simpler functions that we can look at, where we're sandwiching the function we want to look at between two functions that are easier. And so this is saying that suppose g of x, the function g of x, which is in yellow here, is less than or equal to f of x, which is our function in blue, which is sandwiched in between, which is less than or equal to our function of h of x, which is in red. And so if you look at this, the y values, these are all representing y values. You can see the y values of the yellow are always smaller than the y values of the blue, which are always smaller than or equal to the y values of the red. So this says for all values of x in some open interval containing c. So we're just going to sandwich it. Doesn't have to be some interval there. We might get really huge and that wouldn't be the case. expect possibly at x equals c itself, and suppose also that if we're looking at the limit as x approaches c of g of x, the function below is the same thing as the limit as x approaches c of h of x, which is the function above, then we can say the function in between would have to go to the same limit. So looking at this example, it says, if you're given that 2 minus x squared is less than or equal to the function of g of x, which is less than or equal to 2 cosine of x, for all x, what is the limit as x approaches 0 of g of x? Well, let's show that the left-hand piece of this inequality, the limit as x approaches 0 of this piece, which is 2 minus x squared. This would have to be less than or equal to the limit as x approaches 0 of g of x, which would have to be less than or equal to the limit as x approaches 0 of 2 cosine of x. Okay, so we can use our rules of limits. Algebraically, we can just go in here and wherever we see a 0, or wherever we see an x, we're going to plug in 0. And so this piece right here would give us 2 minus 0 squared. We just simplify that. So 2 minus 0 squared is just 2. So this is still, we don't know what this is less than or equal to the limit as x approaches 0 of g of x. Okay, so let's look at the left-hand or right-hand side. So if we go in here and wherever we see an x, we plug in 0 into this function, we get 2 times cosine of 0. Recall cosine of 0 is 1. And so this is less than or equal to 2 times 1, which is 2. And so because the left and the right-hand side of that inequality are the same values, then by the sandwich theorem, if you're looking up information on sandwich theorem, sometimes they call it the squeeze theorem. So they're the same thing, just so you know that. But by the sandwich now I can't even say it. Sandwich theorem, we can say that the limit as x is approaching 0 of g of x then equals 2. Okay, so I know that was a little rushed at the end, but I wanted to give you an example of that sandwich theorem and how it works. And we might use it later on to prove things in future sections. So let me stop.
So if there was a different number on the left side of the inequality and the right side of the inequality, then what would it be like?
So
is there a limit at that point?
We wouldn't know that. It would just kind of tell us that it would actually then have to be limited between those two values, because technically if it's not the same value, you might have, you know, some function on top, the one that we're trying to look like right here or whatever, I don't know, and a more simpler one below. But if you don't get the same value here, I could just say I know that limit as x is approaching c of this middle function would have to be bounded between those, but I don't know that it's going to any one of those values. And so really that sandwich theorem is only going to work if we can get those values on the left and the right to be the same value. And we know that one function is always bigger than or equal to the other one. And the one we want is in between it. So to me, this kind of would be hard if I didn't know what the graphs look like, and I'd have to go and try to think of graphs that might, you know, look the same around the same area. But it's used to prove stuff. Did that clarify it? What you were asking?
Yeah.
Okay. Any other questions? Let me stop the recording.